Hello students, welcome back to my channel. I hope your JEE preparation is going fantastic. Now those who have taken this permutation combination series as a tool for your preparation, I will suggest all of them to see my previous videos before coming to this lecture. Then you will understand the facts more easily. And in every lecture, I will suggest all of you to make a notes so that you can revise those notes before your examination in a very quick interval of time. This is our 5th class on permutation combination, and here we are going to cover combinations from identical objects, problems associated with combinations from identical objects, and dealing with natural numbers. If you are new to my channel, please do subscribe and press the bell icon so that you get notified about all my new videos I upload in this channel. If you really like my video, don't forget to share and like it. So let's move for the class directly. So before starting today's class, let me just do 2 problems which will actually help us for going a quick revision for the previous classes that we have done. The question is, a person is permitted to select at least one and at most n coins from a collection of 2n plus 1 distinct coins. If the total number of ways in which he can select coins is 255, we have to find out the value of n. The person is selecting at least one coin. So one coin can be selected by the person in how many different ways? We are having 2n plus 1 distinct coins. So total number of ways of selecting only one coin will be 2n plus 1 C1. The number of ways in which he can select 2 coins will be 2n plus 1 C2. 3 coins will be 2n plus 1 C3. And this thing will go on. And maximum he can select n coins. So that can be done in 2n plus 1 C n different ways. And according to the problem, this is equals to 255. From this equation, we have to find out the value of n. But what we have learned in the previous class, that is NC0 plus NC1 plus NC2 till NCn, we know this can be written as 2 to the power n. But in our case, in this problem, we cannot write this thing as 2 to the power 2n plus 1. We can't write it that way. Why? Because it has not started with 2n plus 1 C0, number 1. And number 2, it does not go till 2n plus 1 C2n plus 1. Is it clear? Therefore, we cannot use this formula. But to use this formula, what I'm trying to do is, I'm simply multiplying this equation with 2. Both sides, I'm multiplying the equation with 2. So what we are getting? In the left hand side, same thing is there. And in the right hand side, we are getting 2 times 255, which gives us 510. Now, look at very carefully. Now, let me just write this thing. 2n plus 1 C1, 2n plus 1 C2, 2n plus 1 C3, this thing goes on till 2n plus 1 Cn. Then we are having the same thing repetition because I have multiplied the thing with 2. So again you are going to have 2n plus 1 C1, 2n plus 1 C2. This thing goes on till 2n plus 1 Cn. Now, what I'm trying to do here is, let these terms be same, be as it is. So from here we are having this, and now look it carefully. 2n plus 1 C1, this can be written as 2n plus 1 C2n. This can be written as 2n plus 1 C 2n minus 1. And this thing goes on. And the last thing can be written as 2n plus 1 C n plus 1. Why I've written in that way? Because we all know that NCR is same as NCn minus R. So now observe carefully that we can now write the thing in this way. 2n C1, let it be like that. This is 2n plus 1 Cn. Now observe, this thing I'm writing it here. 2n plus 1 Cn plus 1. And before that we are having 2n plus 1 Cn plus 2. And again, before that we will have 2n plus 1 Cn plus 3. And this thing goes on. And the last term will come this. But before that, this term will come. It's 2n plus 1 C2n minus 1. Then we will have 2n plus 1 C2n. Are you getting my point? Which is equals to 510. So we have manipulated the given equation, this one, in this way. But still, we cannot write this thing as 2 to the power 2n plus 1. So for that, what I'm doing, I'm simply adding here 2n plus 1 C0 and I'm adding 2n plus 1 C 2n plus 1. The value of 2n plus 1 C0 is basically 1 and that of 2n plus 1 C 2n plus 1, that is also 1. So I have actually added 2 in the left hand side. So same thing I'm doing in the right hand side. Now your left hand side will transform into 2 to the power 2n plus 1, which is nothing but your 512, which is actually 2 to the power 9. So from here we can write 2n plus 1 is 9, implies 2n equals to 8, implies n is basically 4. Is it clear? Therefore, the required value of n is 4. Have you understood the problem? They have said that the person can select at least one coin and at most n coins. So we are actually having 2n plus 1 distinct coins. Out of there, what are the options that the person has to select the coins? The person have either he can select one coin or 2 coins or 3 coins, still n coins. So it will be written as 2n plus 1 C1 plus 2n plus 1 C2 and this thing goes on till 2n plus 1 Cn. But now to simplify this, we have to use the property of combination. We know that NC0 plus NC1 plus NC2 till NCn is 2 to the power n. So to write that formula, to use that formula, what we have to do? We have to convert this series in this way, 2n plus 1 C0 plus 2n plus 1 C1. This thing goes on till 2n plus 1 C2n plus 1. If you can do that, then only you can write this series as 2 to the power 2n plus 1. That's exactly what I have done. But how I have done? I have simply multiplied 2 with both sides. And then all the terms which is in the left hand side, now it is repeated. Now each term I have used NCR equals to NCn minus R, by virtue of which we are actually getting that series as we have seen. Is it clear? Okay, let's move for the next problem. In this question, they have said in an examination, there are 3 multiple choice questions. Each question has 4 choices. So we are having 3 multiple choice questions. And each question, there are 4 choices. Okay? Each question, it has 4 choices. It's a multiple choice question. Find the number of ways in which a student can fail to give all correct answers. It means what? That the student should not give all the 3 correct answers. Is it clear? Now think about it. The first question can be answered in 4 different ways. The second question can be answered in 4 different ways. And the third question can be answered again in 4 different ways. So the total number of ways the student has to answer these 3 questions, which are each having 4 choices, will be 4 into 4 into 4, that is 64. Now you think about it. There is only one way where this student has answered all the questions correctly. Let us say this answer is correct, this answer is correct, and this answer is correct. So out of these 64 ways, there is one way where the student has marked this answer, and this answer. But in this case, his all answers to these 3 given questions will be correct. But I want that the student should fail to give all correct answers. So I must subtract that option from the total to get the total number of ways of answering these 3 multiple choice questions having 4 choices each, in which the student will fail to give all correct answers. Is it clear to everyone? Have you understood this? Okay, so let's move for the next problem. Answer is 63. In this question they have said, in a city no 2 persons have identical set of teeth, and there is no person without a tooth. Also, no person has more than 32 teeth. If we disregard the shape and size of tooth, consider only the positioning of the teeth. Then find the maximum population of the city. This is the question. Now see, no 2 person can have same number of teeth. Now, a person will have not more than 32 teeth. So the maximum number of teeth that a person can have is only 32. And all of the person will have different tooth. No person is having 2 teeth, or no 2 person will have 3 teeth. It's not happening. All are distinct. All the person will have different teeth. Now, we have to find out the maximum population of the city. It means that we have to find out how many such person are there having different set of teeth. Now, there are 32 places. There are 32 places, right? There are 32 places. Now, in the first place, a teeth can come or it may not come. So there are 2 ways of filling a teeth in the first position. Again, in the same way, the second position can be filled in 2 different ways. Either a teeth is there or it is not there. Similarly, the third position will be filled in 2 ways. Either a teeth is there or it is not there. And the 32nd place in the same way will have 2 ways of filling with a teeth. Therefore, total number of ways in which a set of 32 teeth can be formed is 2 to the power 32. Do you accept this? 2 to the power 32 is the total number of ways in which these 32 places of teeth can be either filled or it is not filled. Now there is one way when no teeth has been placed in any of these 32 places, which is already involved in 2 to the power 32. So that has to be subtracted. Why? Because they have already given. There is no person without a tooth. Therefore, the total number of set of teeth that can be formed, which eventually gives us the population of the city, is 2 to the power 32 minus 1. Hence, option C is correct. I hope this question is very clear to all of you. A person will have minimum 1 tooth and maximum 32 teeth. And no two person are having same set of teeth. So what I've done, I've simply placed 32. There are 32 places. Now each place can be either filled with a teeth or not. So there will be 2 options for every position of the teeth. So total number of ways in which the set of teeth can be formed is 2 to the power 32. Now in this 2 to the power 32, there is one way where there is no teeth in this 32 position. But in the question they have already given that there is no person having no teeth. Am I correct? Therefore, that has to be subtracted from the total number of ways. That is 2 to the power 32. Therefore, the total number of set of teeth that can be formed is 2 to the power 32 minus 1. That is, at least 1 teeth is there, which actually gives us the maximum number of population in that city. Is it clear? Okay, so let's move for today's class and let us start with a new conception. Combinations from identical objects. It's a very, very interesting topic. Very interesting topic. You must understand this by heart. You should be little serious in coming 10 minutes. So the question is, suppose there are 3 chocolates and these 3 chocolates are, let us say, all are distinct. Distinct means, let me just give a name. These 3 chocolates are different. Now my question is, in how many different ways you can give me 2 chocolates from these 3 chocolates? And your answer will be straight away, sir, answer will be 3C2. That is same as 3C1, which is 3. Means there are 3 ways of giving me 2 chocolates from these 3 distinct chocolates. Now, these 3 options can be AB, it can be AC, or it can be B.Sc. That's it. Now see what I'm saying. This we have understood. When the chocolates are distinct. But now, if these 3 chocolates are identical, listen it very carefully. These 3 chocolates are identical. Now if I ask you to give me 2 chocolates, in how many different ways you can give me 2 chocolates out of these 3 chocolates? Now if somebody says, sir, the answer will be in this case 3C2, you will be wrong. Why? The first thing is that we cannot use the formula C here. Because when I have defined C, I told you that out of n distinct objects, you are selecting R objects. Out of n different objects, you are selecting R objects. Distinct objects. Now here, all these 3 chocolates are identical. So you cannot use the formula NCR, that's for sure. So this option is out. Now the question is, in how many different ways you can give me 2 chocolates? Okay, think about this matter in this way, that one person, suppose you have given me this one and this one. I got these 2 chocolates. Now, can I say that which 2 chocolates you have given me from these 3? Or can I go in debate with you that you have not given me that chocolate, you have given me this chocolate? In this case, you can go for the debate. You have got the chocolate A and B. Now somebody can say, sir, you have not received chocolate C. Here you can distinguish because the chocolates are all distinct. But in this case, I cannot fight with you. I cannot go for a debate that why you have not given me that chocolate. Because these 2 chocolates are same, they are identical. Whether you are giving me this one or this one or this one, I don't know. So in this case, 2 chocolates can be given in only one different way. In only one different way. There is no other way of giving me 2 chocolates from these 3 identical chocolates. Have you understood this or not? You are having 3 identical chocolates. I asked you to give me 2. So which 2 you are giving, I did not understand. You have given me any 2. Whether it is the first one or the last one, to me, I cannot distinguish between them because they are identical. Therefore, total number of ways of giving me 2 chocolates will be only one way. Now similarly, if I ask you in how many different ways you can give me 1 chocolate, you will say, sir, again it is only one way. Because whether I give you this one or this one or this one, you cannot distinguish between these 3. I will say absolutely fine. So the total number of ways of giving me 1 chocolate is one way. Giving me 2 chocolates is again in one way. And even if I ask you in how many different ways you can give me 3 chocolates, you will again say, sir, the answer is one way. So there is, if you give me chocolates, if you give me 1 chocolate, that will be in one way. 2 chocolates again in one way. 3 chocolates again in one way. Now, if you don't give me any chocolate, that can also happen in one way. That way is that where you are not giving me any chocolate. Therefore, if I ask you, listen it carefully, very minutely you listen it. If I ask you in how many different ways you can give chocolate to a person, in how many different ways you can give chocolate to a person where you are having 3 identical chocolates, your answer will be no chocolate is given in one way, 1 chocolate is given in one way, 2 chocolates given in one way, and 3 chocolates given in one way. That is, there are 4 different ways. There are 4 ways in which you can give chocolate to someone. Now that chocolate can be 1 chocolate or 2 chocolates or 3 chocolates or no chocolates. Now if I simply give a little twist in this problem and if I say that at least 1 chocolate you have to give, in that case you will say, sir, this one I have added, this one was the way where I have given you no chocolate. So now in this question, now what I am saying that at least 1 chocolate you must give. So what I will do, I will simply subtract 1. That one way, I will subtract it from this total way. So we will have 3 ways of giving this chocolate to a person, where at least 1 chocolate is given. If I ask you in how many different ways chocolates can be given, you will say there are 4 different ways. But if I say in how many different ways, at least one chocolate is given, all are distinct. Again, I'm telling you, all are identical. They are not distinct. All are identical. So there you will say, sir, the total number of ways when at least one chocolate is given will be 3 different ways. That's it. Have you understood the thing? Is it clear? Now, this thing is not happening in case of when the chocolates are distinct. Because in distinct chocolates, if I ask you that no chocolate is given, in how many different ways you can do that? It is 3C0. If I ask you, one chocolate will be given from 3 distinct chocolates, in how many different ways you can give that? It will be 3C1. 2 chocolates, 3C2. 3 chocolates, 3C3. So in that case, the total number of ways will be 3C0, 3C1, 3C2, or 3C3. That gives us 2 cube, which is actually 8. So 8 is the total number of ways when 3 chocolates are distinct, and the total number of ways in which you can give those chocolates, out of which there is one case where no chocolate is given to that person. Are you getting my point? So that is when the chocolates are distinct. But in case of identical, the scenario is different. The scenario is different. Why? Because the chocolates are identical. No chocolate is given in one way. One chocolate is given in one way. 2 chocolates are given in one way. And 3 chocolates are given in one way. So there will be 4 ways of giving those chocolates, in which there is one way when no chocolate is given. That is also a selection. But if I give you this question in such a way that if I say that at least one chocolate you have to give, in that case what you will do, from this total ways, that is the 4 ways, you will simply subtract that one. Which one you are subtracting? The case where you have not given any chocolate. That case is subtracted from this total ways to get the total number of ways in which at least one chocolate is given. Is it clear to everyone? Now, if I generalize this, suppose if we are having in identical objects, and if I ask you how many different ways these objects can be given, it will be n plus 1 different ways. Just now I have explained, when 3 identical chocolates were there, the total number of giving those 3 chocolates were 4 ways. So in this case, there are n identical objects. So the total number of ways of giving those identical objects is n plus 1 ways. Now if I ask you that at least one object has to be given, in that case, the total number of ways will be n ways. Are you getting my point? Have you understood this problem clearly? I mean, this conception clearly? Okay, let us take some problems based on this. In this question, they have said there are 4 oranges, 5 apples, and 6 mangoes in a fruit basket, and all fruits of same kind are identical. That is, your 4 oranges, they are identical, your 5 apples are identical, and at the same time 6 mangoes are identical. Now what's the question? In how many ways can a person make a selection of fruits? In how many ways a person can make a selection of fruits? It means that you have to select at least one fruit from this basket. Now we are having 4 oranges, and 4 oranges can be selected in how many different ways? 4 plus 1, that is 5 different ways, in which you can select no orange, or 1 orange, or 2 oranges, or 3 oranges, or 4 oranges. Is it clear? So there are total 5 different ways of choosing oranges. Is it clear? There are 5 apples, so it can be selected. I mean, the apples can be selected in how many different ways? 5 plus 1, that is again 6 different ways. And we are having 6 mangoes which can again be selected in how many different ways? 7 ways. Therefore, total number of selections. Total number of selections will be what? 5 into 6 into 7. That is 35 into 7. That gives us, so 5, 6, the 30 into 7. That gives us 210. Now, in this 210 ways of selecting fruits, there is one way where you have selected neither apple, nor orange, nor mango. So that has to be subtracted from this total way. Why? Because at least one fruit has to be selected. Is it clear? Therefore, the total number of ways will be, total number of ways where at least one fruit is selected is 209. Is it clear to all of you? Have you understood the problem clearly? Whenever you are saying that there are 5 objects, in how many different ways you can select these 5 objects? There will be 6 different ways. In these 6 different ways, there is one way when you are not selecting that object. That is also included. So whenever they ask that at least one object is selected, so you have to subtract that option from the total number of ways. That's exactly what I have done here. Is it clear? Let's move for the next problem. See this question. There are P copies each of n different books. So let us say this is book 1, this is book 2, book 3, and this thing goes on. This is book n. And each one, it has P copies. Okay? P such copies are there. Okay? Can we denote this thing by P1, P2, P3? No, we cannot denote those copies as P1, P2, P3. Why? Because all those copies are identical. For the book B1, all the copies associated with book B1, they are identical. All the copies, all the P copies of book 2, they are identical. Similarly, for book 3, they are identical. Are you getting my point? And even for book N, all the P copies of book N, they are identical. These are all identical. So in how many different ways a non-empty selection, be careful, non-empty selection means you have to select one copy. It can be from anywhere, from book 1 or book 2 or book 3, whatever, but at least one copy has to be selected. Now see this one. For book 1, there are P copies. In how many different ways you can select those P copies? It is P plus 1 different way. Isn't it so? Why P plus 1? Because you can either select 1 or 2 or 3 or P copies at a time. But every time, this selection will be exactly in one way. If I want to select 2 copies, it will be in one way. If I want to select P plus 1 copies, P copies, it will be again in one way. And even if I don't select any copies, that will be also in one way. So total number of ways for book 1. To select a copy from book 1, it will be P plus 1 different ways. Is it clear? Now the similar thing will happen for B2. There are P copies. So that can be selected in P plus 1 different ways. Similarly for B3, book 3. And this thing goes on till for book N. So total number of ways of selecting copies will be P plus 1 whole to the power N. But in this total selection, there is one selection, only one selection. When you have not selected copies from B1 or B2 or B3 or B4 till Bn. That is, you have not selected any copy is one way among this P plus 1 whole to the power N. Is it clear to you? Therefore, total number of non-empty selection will be P plus 1 whole to the power N minus 1. So that will be our answer. I hope this question clears your conception that I taught you right now. Okay? So let's move for the next question. In this question, they have said that find the number of words that can be formed by taking 4 alphabets from the words mathematics. Now, it is actually a question of permutation as well as combination that we will see. In mathematics, there are 2 M's, there are 2 A's, and there are, anything repeated? Yes, T, 2 T's are there. And rest are all different. H, E, I, C, and S. These are all distinct alphabets. But 2 M's are there, 2 A's are there, and 2 T's are there. Now the question is, in how many different ways you can form words by taking 4 alphabets from this word? Now we have to consider some cases here. Case 1. First you have to select 4 alphabets out of this 11 alphabets which actually forms the word mathematics. There are 11 alphabets here. Okay? So case 1 is we have to first select 4 alphabets. Now first we are considering that all the alphabets are distinct. All alphabets are distinct. Now, how many distinct alphabets you have? You have 1 M. From this 2 M, I can select 1 M. 1 A, 1 T, H, E, I, C, and S. So how many alphabets now you are having? 1, 2, 3, 4, 5, 6, 7, 8. So out of these 8 alphabets, first you are selecting 4 alphabets. And after getting these 4 alphabets, you have to form words. So you have to arrange these 4 alphabets in 4 places. And that can be done in factorial 4 different ways, which is same as your 8p4. Am I correct? Okay, so now let us consider case 2, in which 2 alphabets are identical and 2 distinct. Now the question is, 2 alphabets are identical. Which 2 alphabets which are identical? So out of these 3 alphabets which are available, which are actually occurring in pairs, we have to select only 1 pair. Out of these 3 pairs, M, A, or T, you have to select only 1 pair, because the moment you select 1 pair, you are actually getting 2 alphabets which are of identical. Is it clear? So in how many different ways you can select 1 pair out of these 3 pairs? That can be done in 3C1 different ways. Is it clear? Now let us assume that we got M. Now how many distinct alphabets are available right now? 1 is A, T, H, E, I, C, and S. So we are having 7 distinct alphabets, out of which you have to choose 2. Then what will happen? You are going to have in this, what is the selection? In this 4 alphabets which you have selected, 2 are identical and 2 are distinct. Now you got 4 alphabets. Now you have to form the word. So what you will do? These 4 words will arrange among themselves in factorial 4 different ways. But two alphabets are identical, so it has to be divided by factorial 2. Is this clear or not? Okay, what other case is possible? Case 3. Two alphabets are identical of one kind and two alphabets are identical of another kind. Okay? That means what? You are actually selecting two groups from these three pairs. I mean, you are actually choosing two pairs from these available three pairs. Yes or no? Because the moment you choose one pair, you are actually having two identical alphabets. Since you need two alphabets identical of one kind and two alphabets identical of another kind, so what I'm doing, from this available three pairs, I'm selecting two. So that can be done in 3C, two different ways. Now the moment you get these two pairs, now you are having four alphabets in your hand. Now these four alphabets can arrange among themselves in factorial 4 divided by. Two alphabets are identical of one kind, so it is divided by factorial 2. And two other alphabets are identical of another kind, so it has to be divided by factorial 2. That's it. Therefore, the total number of words such formed will be this one plus this one plus this one. Is it clear or not? So let me just go for quick calculation. So this is factorial 8 divided by factorial 4. So that gives us 8 into 7 into 6 into 5 into factorial 4 divided by factorial 4. So this gives us 7 8s are 56 into 30, which gives us actually 1680, right? Now this one is basically 3 into 7 into 6 divided by 2 into 4 into 3 into factorial 2 divided by factorial 2. So we are having, so actually it is coming 7 3s are 21 into 3 and this is 12, right? So it is coming like 21 into 36, so that gives us 756. And from here we are getting, this is 3, this is 24 divided by 2 into 2. So it is 3 into 6, that is 18. Therefore, the total number of such words, 4 alphabet words, which can be formed from the word mathematics is 1680 plus 756 plus 18. That gives us 2454. And that's the answer. Is it clear to everyone? Have you understood this? So actually, this problem is a mixture of permutation and combination. First, we are considering the cases because here all the alphabets are not distinct. Some are identical, some are distinct. So we have to consider cases because first we have to select 4 alphabets. So what kind of alphabets you are choosing? In that selection, are you getting any repeated alphabets? That you have to check first. And that's the reason why I have considered cases. The first case I have considered that no alphabets are repeated. Next case I have considered that 2 are repeated alphabets and other 2 are distinct. And next we have considered that we have considered 2 pairs in which 2 are identical of one kind and 2 is identical of another kind. Getting my point? And then we have added all those cases to get the total number of words, required words formed. Okay? Now let's move for a new conception. Combinations when both identical and distinct objects are present. Now, so far whatever we have discussed in today's class is that objects were identical. But in that, we have not combined that there are certain numbers certain alphabets or certain objects which are not identical. They are distinct. So in that case, how many different ways are there of selecting objects? Let me take an example. Let us say we are having 3 A's, 4 B's, 2 C's, and let us say D, E, F, G. These are all distinct alphabets. Here there are 3 identical A's, 4 B's are repeated, and 2 C's are identical, right? Now my question is, in how many different ways alphabets can be selected? In how many different ways alphabets can be selected? These 3 alphabets can be selected in 3 plus 1, that is 4 ways. Yes or no? These 4 B's can be selected in 4 plus 1, that is 5 ways. These 2 C's can be selected in 2 plus 1, that is 3 ways. Yes or no? Therefore, only these objects can be selected in how many different ways? 4 into 5 into 3 different ways. Are you with me? Now, what about this D, E, F and G which are distinct? See, in our selection, this D has 2 options. This D has 2 options. Either it can come or it may not come. E has again 2 options. Either it can come or it will not come. Similarly F and similarly G. So for every distinct alphabets, there are 2 possibilities. Either it will be selected or it is not selected. So for these 4 distinct alphabets, the total number of ways in which they can be selected is 2 to the power 4. Am I correct or not? 2 options for D, 2 options for E, 2 options for F and 2 options for G. Therefore, total number of selection will be this. If they ask you what is the total number of selecting alphabets, then your answer will be 4 into 5 into 3 into 2 to the power 4. That's it. But if the question is, at least one alphabet has to be selected, be very careful about this particular term. When they say at least one object, at least one, in this case, at least one alphabet is selected. In that case, the option where you have selected no alphabets should be subtracted from the total one. So in this case, when they say at least one alphabet is selected, then your answer will be 4 into 5 into 3 into 2 to the power 4, because this involves one case where no alphabet is selected. So that case has to be subtracted from here to get my final answer. I'm not going for calculation. Try to understand. That is why I'm showing it. Is it clear? So that particular option has to be subtracted. So now I think you people are all comfortable with the identical objects, with the distinct objects. Distinct objects you are already comfortable because you have all seen my previous classes. So distinct objects, it's okay. Today we have learned if there are identical objects, what to do. And now we have seen that if there are identical as well as there are distinct objects, how to deal with those kind of problems. Remember, when they are saying how many number of selection can be done, in that case, not selecting anyone is also considered. But when they say that at least one alphabet or a non-empty set to be selected, it means that at least one object is selected. So what I will do, from the total number, I will subtract that option where you have selected no objects given to us. And then you are going to get the final answer. Is it clear? Okay, let's move for the next part. So now we are going to learn a new thing, that is finding out the number of divisors of n. This n is basically a natural number. Now we all know that any natural number can be expressed as a product of prime. This is what is called your prime factorization. Is it clear? It means that you choose any natural number, and that natural number can be expressed as a product of prime. Like, let us take an example of, let me take a very small number, let us say 12. Now 12 can be written like what? It can be written like 2 square into 3. See? This 12 is a natural number which has been expressed as a product of primes 2 and 3. Is it clear? Let me take another example like 60. This can be written as 2 square, that is 4 into 3 into 5. Again, 60 has been expressed as a product of primes. Is it clear or not? Now the question is, how many number of divisors of this natural number 12 is there? Let us try to think in this way, that what are the divisors or factors? All same. How many number of divisors or factors of 12 exist? The factors can be 1, 2, 3, 4, 6 or 12. Is it clear or not? So these are the 6 factors or divisors of 12. Similarly, if we see 60, what are the divisors? It is 1, 2, 3, 4, 5. It can be 6, 7, 8, no, 9, 10, yes, 12, 15, then coming to 20, then 30, then 60. Am I correct or not? So there are 12 divisors or factors of the natural number 60. So now we have to find out. You see, in this case we can calculate, we can find out. But if the number is very big, so we cannot find out factors in that way, or it will take a lot of time. In some cases, it may be impossible to calculate this thing manually. So definitely we have to develop some system. Okay, let's see this 12. We are having 2 square. Now let me consider 2 sets. Let us consider 2 sets. In the first set, we are having all the possible powers of 2 within 2 square. That can be 2 to the power 0, 2 to the power 1 or 2 square. Now in the second set, we are considering all the possibilities of this 3 to the power 1. I mean all the factors like 3 to the power 0 or it can be 3 to the power 1. Now observe carefully, very carefully. If we choose any one element from this set and any one element from this set, then we are going to have a factor or divisor. Tell me yes or no. Suppose if I choose 2 to the power 0 and if we choose 3 to the power 0, then 2 to the power 0 and 3 to the power 0, it is a factor of 12. Yes, it is true. 2 to the power 0 is 1, 3 to the power 0 is 1. So it is 1. 1 is a factor. Now if we choose 2 to the power 0 and 3 to the power 1, again we are going to have another factor. Check it. It's 1 into 3 that gives us 3. Yes, 3 is a factor. Now if we consider 2 to the power 1 and 3 to the power 0, we are having 2 into 1, that is 2. Yes, 2 is a factor. Similarly, 2 to the power 1 into 3 to the power 1, that gives us 6. 6 is a factor. 2 square into 3 to the power 0. 2 square is 4 and 3 to the power 0 is 1. So 4 is a factor. 2 square into 3 to the power 1. That is 4 into 3, that is 12. Again, 12 is a factor of this number, natural number 12. So, how many number of divisors or factors are there? We simply find out how many number of elements are there in, let me just give a name, A and B. How many number of elements are there in set A and how many number of elements are there in set B? So in this case, we can see that in set A we are having 3 elements and in set B we are having 2 elements. Therefore, there will be 6 factors or divisors, and which is true. Have you got it? In 12, we got 2 square into 3. So 2 square, I'm just writing it in 2 sets. We are having 2 primes, we are writing 2 sets. One set consists of 2 to the power 0, 2 to the power 1 and 2 square. And another set consists of 3 to the power 0 and 3 to the power 1. So total number of factors or divisors will be nothing but the total number of elements in set A into the total number of elements in set B. Tell me yes or no. Let us check for 60. In 60 we have to consider here 3 sets. Why? Because there are 3 primes. In the first set, A, we are considering all the possibilities of 2 square. So it is 2 to the power 0, 2 to the power 1, 2 square. In the second set B, we are considering all possibilities of 3 and they are 3 to the power 0 and 3 to the power 1. And we are considering for set C, 5 to the power 0 and 5 to the power 1. Now, total number of factors will be, or total number of divisors of 60 will be, here there are 3 elements, here there are 2 elements, and here again there are 2 elements. Therefore, total number of divisors or factors will be 3 into 2 into 2, that gives us 12. And you see, we got 12 divisors here. Is it clear to everyone? Is this clear to everyone? How to find out the number of divisors or factors of n? Let me take any natural number n. And let us say that this n, when goes for prime factorization, we are getting something like this. 2 to the power alpha 1, 3 to the power alpha 2, 5 to the power alpha 3, and let us say 7 to the power alpha 4. Now if I ask you how many number of divisors of n, of this n, is possible? Refer to the previous example, see this one. In this case, how many number of factors or divisors were there? 12. How we got? 3 into 2 into 2. How this 3 is coming? If we see, we will find that the exponent of 2 is 2. Therefore, number of elements in set A will be 2 plus 1. The exponent of 3 is 1. Therefore, the number of elements in set B, you observe, there are 1 plus 1, that is 2 elements. Again, in case of 5, it is 1. So, the number of elements in set C are 1 plus 1, that is 2. So, it gives us 3 into 2 into 2. Is it clear? Which eventually gives us 12. Same thing here, 2 square. So, it is 2 plus 1 and 3 to the power 1. So, it is 1 plus 1. So, total is 3 into 2. That gives us 6 such divisors or factors. So when your n is written in prime factorization like 2 to the power alpha 1, 3 to the power alpha 2, 5 to the power alpha 3 and 7 to the power alpha 4, then total number of divisors or factors total number of divisors or factors will be how much? It is alpha plus 1, alpha 2 plus 1, alpha 3 plus 1 and alpha 4 plus 1. That's it. Is it clear to everyone? Is this clear to everyone? So for any natural number, first, if they ask you how many number of factors or divisors are there, you simply go for prime factorization of that natural number which is given to us. And after doing that, after completing the prime factorization, you see what are the exponents of that prime numbers which are involved in that the product of that natural numbers. So all you do is you simply add 1 to each of the exponent and multiply to get the total number of divisors or factors. Is this clear to everyone? Have you understood? Okay, let me take one problem. Let us see this question. Find the number of divisors of the number 17640. So my first task is to go for prime factorization of this number 17640. I have already calculated it and I'm writing it here. 17640 can be written as 2 cube into 3 square into 5 to the power 1 into 7 square. Now if they ask you how many number of divisors are there, divisors or factors are there, what you will say? You will simply say the total number of divisors will be 2 plus 1. So that gives us 4 into 3 into 2 into 3. So that gives us 6. So 72. So how many number of divisors of 17640 are there? You will simply say that there are 72 factors or divisors of 17,640 are there. Is it clear or not? Absolutely. Okay. Let's see the next problem. First is over. Second says, find also the proper divisors of 17640. Now the question comes, what is proper divisor? Before knowing proper divisors, we must know what is improper divisor. Improper divisors are those numbers, there is, for any natural number, there is always 2 improper divisors. And these 2 improper divisors are 1 and the number itself. Is it clear? So how many number of proper divisors are there? The total divisors minus the number of improper divisors will give us proper divisors. Now we saw that for 17,640, we got 72 divisors. Now if I ask you how many number of proper divisors are there? From this total number, let me just write it here. Proper divisors will be how much? 72 minus 1 and minus the number itself. Because if you multiply all these numbers, you are going to have 17640. And that is one factor which is very much involved in 72. As well as 1 is also involved in it. Yes or no? 1 is also in, because 1 is a factor. 1 is a factor. Yes or no? So which both of them, 1 as well as that number, is included in 72. So to get proper divisors, we have to subtract these 2 improper divisors from the total divisors, which in this case is 72. Therefore, total number of proper divisors will be 70. Is it clear or not? Absolutely. Okay. See the next question. Find the number of even divisors. Very interesting. Very, very interesting. For this number, 17640. Now let me do one thing. Simply apply your common sense. Let me just draw 4 sets. Because there are 4 primes for 17640. So we have drawn 4 sets, A, B, C, D. Look it very carefully. Your set A consists of 2 to the power 0, 2 to the power 1, 2 square and 2 cube. Set B consists of 3 to the power 0, 3 to the power 1, 3 square. 5 to the power 0, 5 to the power 1, again 7 to the power 0, 7 to the power 1 and 7 to the power 2. Now think about it. I want even divisors. Now, where do you get even divisors? When in the factor you have 2. When in any factor you have 2, it's an even divisor. So I have to find out that. So what to do? So what I will do in this case is, I will not consider this element of set A. I am not going to consider this element in set A. That is 2 to the power 0. 2 to the power 0 means what? It's 1. So when that 1 is multiplied with any of the elements chosen from B, C and D, it is not going to give you an even number. That is, you are not going to get an even divisor. So what I'm trying to do here is, I'm simply rejecting 2 to the power 0. I'm not considering that. So total number of divisors that can be formed is that you can choose any one element from these 3 elements from set A, excluding 2 to the power 0. So there are 3 ways of choosing one element from set A. 3 elements from B, 2 elements from C, and again 3 elements from D. So total number of even divisors or factors, whichever way we say, total number of even divisors will be 3 into 3 into 2 into 2. That gives us 54. Am I correct or not? Have you understood the problem? They have said you have to form even divisors. Even divisors means what? In the factor you must have at least 1 2. So if you consider 2 to the power 0 into your calculation, so all the digits that are formed with 2 to the power 0 means there is no 2 present in the factor. That means it is not an even divisor. So to get the even divisor, what I have done, I have simply excluded 2 to the power 0. That is, whatever factor you are choosing, at least 1 2 is coming. That means it's an even divisor. That's it. Now see the second part. You have to find out the number of odd divisors. Now, one way of doing that, because you see, your divisors can be either even or odd. No other option left. So one way of doing this one is, method 1, you know the total number of divisors, that is 72. And if you subtract total number of even divisors, which is 54, we are going to have 18 divisors, and eventually these 18 divisors are all odd divisors, right? Because what you have done, from the total number of divisors, you have simply subtracted the even number of divisors. So you got your answer as odd number of divisors. As simple as that. This is one way of doing. Now, if we try to do it logically, how we will do? You see, it is an odd divisor. It means what? That now I will not select 2 to the power 1, neither I will not select 2 to the power 2 or 2 to the power 3. Because if you choose any one element of this 3, it is going to become an even divisor. So not to get, the even divisor, you should avoid taking 2's. In the divisor, there should not be any 2 present. So that's the reason from set A, I have excluded 2 to the power 1, 2 square and 2 cube. Now you are left with only 2 to the power 0 and 2 to the power 0 is 1. That is, whatever factors you are taking from B, C and D, it is multiplied with 2 to the power 0, that is 2 to the power 1. It means you are always getting an odd divisors. Yes or no? Because there is no 2 present. So total number of divisors in that case will be, from set A you will choose only one element. From set B it is any of these 3. From set C it is any of these 2, any one of these 2. And from set D it will be any one of these 3. So from here also you are getting 18. Is it clear? So I have done this problem in 2 ways. Either you do one thing, you find out the total number of divisors, and then you find out even number of divisors, and then you subtract to get the odd divisors, which is actually useless. Why should you go? If suppose only they have asked for to find out the odd divisors, why should you go for finding out the total number of divisors, then even divisors, then you are subtracting? That is useless. So all you will do is, you will simply adopt method 2. And what I have done in method 2? Since odd divisors they have said, so simply I am not going to take any 2. So from set A, I have rejected 2 to the power 1, 2 square and 2 cube. So we are left with 2 to the power 0. Every time I am taking 2 to the power 0 from set A. So when you take 2 to the power 0, that means you are taking only 1. And whatever digits are coming from the other sets, there is no even, because they are all primes. Primes means they are odd. So when you are multiplying the odd numbers, you are always going to get an odd number. So you are definitely going to get odd divisors. Is it clear now? So when it is an even divisor, when they are asking for even divisor, try to eliminate 2 to the power 0. Don't take 2 to the power 0. Otherwise, there will be no 2 there. So no even divisors you will get. And if they ask for odd divisors, you simply reject all the possibilities of 2 except 2 to the power 0. Is it clear to all? Okay, let's move for the next one. So these are the 6 more parts of the same question. The first part says, how many divisors are perfect squares? 17,640, the number that we have. Now we got that there are total 72 number of divisors are there. Now the question is, how many such divisors are there which are perfect square? That we have to find out. So now, before directly involving in the question, let us just try to give you a logic. The logic is, for any square number, if it is any number which is a perfect square, you choose 81, or you choose 36, or you choose 49, whatever, you always see that it is always, the exponent is always an even number. It is always an even number. Whenever it is a perfect square, the exponent is always an even number. Is it clear to us? Absolutely. Okay. So now, in 17,640, let me just draw first 4 sets over here, because we are having 4 primes. And we are having 2 to the power 0, 2 to the power 1, 2 square, 2 cube. 3 to the power 0, 3 to the power 1, 3 square. 5 to the power 0, 5 to the power 1, 7 to the power 0, 7 to the power 1, 7 to the power 2. Now, if we multiply all those elements, that is, here there are 4 elements, 3, 2 and 3. And if you multiply this, we have already calculated this, we got 72. That is, total number of divisors are 72. Now the question comes, how many of these 72 divisors are perfect squares? So just now we got the logic that for finding out or getting any number which is perfect square, the exponent should be always even. So in this case, from the first set, we are rejecting 2 to the power 1. We are rejecting 2 to the power 3. Are you getting the point? I am considering only 2 elements from the first set, which is 2 to the power 0 and 2 square. That is, we have only considered the even exponent of 2. So here we are having 2 to the power 0 and 2 square, because whatever divisors we will get after multiplying, the elements that are will be chosen from the separate sets A, B, C, D. After multiplying, if the exponent is even, we are always going to get a perfect square. That you accept, because just now we have seen that for any perfect square, the exponent is always an even number. So from set A, I am going to select either of these 2 elements, either 2 to the power 0 or 2 square. Similarly, from set B, I am going to reject 3 to the power 1, because the exponent of 3 in this case is 1. So I am going to reject it. I am going to take only those exponents which are even. Again, from here 5 to the power 0 is rejected. From here 7 to the power 1 is rejected. So now you observe carefully that from the first set we are getting 2 elements, either 2 to the power 0 or 2 square. From set B we are again getting 2 elements. From set C we are getting 1 element. And from set D again we are getting 2 elements. So total is 8. Now 8 will be the total number of divisors which are perfect square. Let us take one example. Let me take, I have chosen say 2 square from here, 3 to the power 0 from here, 5 to the power 0, and let us say 7 square. Now look at carefully. It is what? 2 square, 4, 1, 1, 49, right? So it is nothing but 14 square. Yes or no? So 14 square is basically the divisor, and which is nothing but a perfect square. So that divisors I want, which is a perfect square. So what logic we have learned? We have learned that from the sets, we are going to reject all the exponents of the primes whose exponents are not even. We are going to reject that, and we are only going to take the exponents, the exponents of the primes which are even. And then only after multiplying, you are going to get the divisors which are all perfect square. Is this clear to everyone or not? Please tell me this. Absolutely clear? Okay, let's move for the next one. It says that find the sum of all the divisors. Now, a very interesting thing. Find the sum of all the divisors. How many number of divisors we got for 17640? It was 72. Now the question is, all these 72 factors or divisors that we got, I want to add them up. I want to find out their summation. I mean, if you add all those divisors, what will be the answer? That's the question. How to do that? To understand this logic, let me take one natural number which we have already taken in the beginning of this part. 60 we have written in this way, 2 square into 3 into 5. If you can understand the logic that I am going to establish here, the moment you understand this logic, it will be pretty simple for us to calculate or to find out the sum of all the divisors when this natural number is given to us. Now in this case, if we consider, let me just do it analytically first, then only you will understand. So these are my three sets ABC. Here there are 2 to the power 0, 2 to the power 1, 2 square, 3 to the power 0, 3 to the power 1, and it is 5 to the power 0 and 5 to the power 1. So now, I want to find out the sum of the divisors. First, what are the divisors? 2 to the power 0 into 3 to the power 0 into 5 to the power 0. This is one divisor of 60. The another one is 2 to the power 0, 3 to the power 0, 5 to the power 1. Is it clear? Next we are considering 2 to the power 0 into 3 to the power 1 into 5 to the power 0. Then again we are considering 2 to the power 0, 3 to the power 1, 5 to the power 1. Is it clear? Is this clear? So these are the four divisors that we got. What are the other divisors? Now choose 2 to the power 1 multiplied with 3 to the power 0. I am writing all the divisors in all possible ways. Into 5 to the power 0. Then 2 to the power 1. 3 to the power 0 into 5 to the power 1. 2 to the power 1. 3 to the power 1 into 5 to the power 0. 2 to the power 1. 3 to the power 1 into 5 to the power 1. Now consider 2 square. 3 to the power 0, 5 to the power 0. 2 square. 3 to the power 0, 5 to the power 1. 2 square. 3 to the power 1, 5 to the power 0. 2 square. 3 to the power 1, 5 to the power 1. Is it clear? So there are 12 divisors that we have already seen, because we can easily see the total number of divisors will be 1 plus 2 into 1 plus 1 into 1 plus 1. That gives us 12. So 12 such all divisors are written over here. And we want to find the sum. That is why I have added all those divisors. Now, if I add this, look at very carefully. If I add this, we are going to have 2 to the power 0 plus 2 to the power 1 plus 2 square into 3 to the power 0, 5 to the power 0. Then again, if I take 3 to the power 0 into 5 to the power 1 common, we are left with 2 to the power 0, 2 to the power 1, 2 square, 3 to the power 0, 5 to the power 1. Then again from the third column we are getting 2 to the power 0, 2 to the power 1, 2 square into 3 to the power 1 into 5 to the power 0. And for the fourth column, we are getting 2 to the power 0, 2 to the power 1, 2 square into 3 to the power 1 into 5 to the power 1. That's it. Okay. Now from these four factors, let me take this common. Okay. So what we are left with? 3 to the power 0, 5 to the power 0 plus. Right? So in this case, again, from this 2, if I take 3 to the power 0 common, we are left with 5 to the power 0 plus 5 to the power 1 plus 3 to the power 1 if I take common. So we are left with 5 to the power 0 plus 5 to the power 1. Now let me take common 5 to the power 0 plus 5 to the power 1. We are left with 5 to the power 0 plus 5 to the power 1 into 3 to the power 0 plus 3 to the power 1. That's it. Is it clear? So what we have seen, when the exponent is 2, 1 and 1, then the sum of all the divisors will become, since there is 2 square, how we have written? How we got actually, not written, how we got. We got the thing like 2 to the power 0 plus 2 to the power 1 plus 2 square. Now 3 to the power 1 is there. How we got? We got 3 to the power 0 plus 3 to the power 1. Then again 5 to the power 1 is there. So how we got? We got 5 to the power 0 plus 5 to the power 1. That's it. So what will be the sum of this? This is actually 137 into 6 into 4. So 7 6 are 42 into 4. That gives us 168, right? So that will be the sum of all the divisors. So what we have understood, can we establish a formula from here? If we write that your n is, some natural number n is, let us say 2 to the power alpha 1, 3 to the power alpha 2, 5 to the power alpha 3, and this thing, let us say 7 to the power alpha 4. That's it. Okay. Now, if I ask you that how many number of divisors are there, you will easily say, sir, the total number of divisors will be this. Right? Total number of divisors will be this. Now, I want to add all those divisors. Then what will be your answer? Your simple answer will be, sir, it will be 2 to the power 0, 2 to the power 1, 2 square, and this goes till 2 to the power alpha 1, into 3 to the power 0 plus 3 to the power 1 plus 3 square, and it goes till 3 to the power alpha 2. Then it is 5 to the power 0, 5 to the power 1, 5 square, till it goes to 5 to the power alpha 3, and 7 to the power 0 plus 7 to the power 1, 7 square, till goes 7 to the power alpha 3. So whatever answer we are getting from here, multiplied with this one, multiplied with this one, and multiplied with this one, will give us the sum of all the divisors of that natural number n. Is it clear to everyone? So we will treat this thing as a formula, right? Now let us come to the question. We have been said 17640. Total number of divisors are 72. Now I want to find out the sum of all the divisors. So what I will do, straight away I will write that the sum of all the divisors, sum of all divisors or factors, whichever way you say, will be what? 2 to the power 0 plus 2 to the power 1 plus 2 square plus 2 cube. 3 to the power 0, 3 to the power 1, 3 square. 5 to the power 0, 5 to the power 1. 7 to the power 0, 7 to the power 1, and 7 square. That's it. So that will give us what? This will give us, this is 15 into 3 to the power 0, 9, 12, 13 into 6 into 57. So the sum is coming to 66690. Is it clear? Calculation, you check it, but you have to understand the fact behind it, how we are going to solve this kind of problems. So whenever sum of all the divisors are asked, we will simply see what is the exponent of the primes. Suppose if the exponent of the prime 2 is 3, so we will simply add 2 to the power 0 plus 2 to the power 1 plus 2 square plus 2 cube. And then we will find out the exponents of the other primes. In the similar way, we will multiply everything to get the sum of all the divisors. Is it clear to everyone? Absolutely clear? Okay, let's move for the next problem. So, find the sum of all the divisors. This we have already completed. Now, a very interesting thing. Find the next problem. Find the sum of all the even divisors. Then the next question is find the sum of all odd divisors And the next question is find the sum of all proper divisors. We will do these three things at a time. Okay? So now see this one. Find the sum of all the even divisors. Think about it. What is even divisor? Even divisors are those divisors in which your 2 is present. At least one 2 is present. Tell me yes or no. You okay? Now see this question. They have said find the sum of all the even divisors. So to find out the sum of all the even divisors, our first task is to find out what are the even divisors. The moment we get the number of even divisors, we can easily add them up. Now, for that, let me just draw first 4 sets again. This set method helps us a lot. Okay, so these are my 4 sets. This is A, B, C and D. Now here there are the elements like 2 to the power 0, 2 to the power 1, 2 square and 2 cube. Here it is 3 to the power 0, 3 to the power 1 and 3 square. 5 to the power 0, 5 to the power 1 and 7 to the power 0, 7 to the power 1 and 7 square. Now to find out the even divisors, we have already discussed this. The divisor should have at least 1 2. It must have 1 2. At least 1 2 it must contain. In that case, we will say that the divisors are even. Okay? So for that one, what I will do, I will straight away reject this one. I will straight away reject 2 to the power 0. Why? Because 2 to the power 0 is basically 1. And if that 1 is multiplied with the other factors or other elements from the sets B, C and D, it will give us an odd divisor. But I need only even divisors. So for that, I am rejecting 2 to the power 0. So now you tell me, as we have learned in the formula, how to find out the sum of all the divisors? We have simply added in this fashion, right? Depending on what is the exponent of the prime. So same thing here we will do. In this case, for 2, there are only these 3 elements to be taken. So it will be 2 to the power 1 plus 2 square plus 2 cube into 3 to the power 0 plus 3 to the power 1 plus 3 square. I don't have any restriction about the other primes. I'm least bothered about that because that is not going to create even divisor. The even divisor will be created when the divisors will contain at least 1 2. So for 5 we are having 5 to the power 0 plus 5 to the power 1. And for 7 we are having 7 to the power 0, 7 to the power 1 plus 7 to the power 2. And that is the formula just now we have learned. So the sum of all the even divisors will be, from here we will get 2, 4, 14 into 13 into 6 into 57. Am I correct? So the answer is coming to 62244. Okay? So this is the sum of the even divisors. Have you understood the problem? What we have done? They have said to find out the sum of the even divisors. Just now we have learned how to find out the sum of all the divisors. That we have learned. And we have established a formula also at the same time. Now in this case, to find out the even divisors, what we need? We need that in the factor there should be at least 1 2. And for that reason, I have rejected 2 to the power 0 because 2 to the power 0 is 1. And in that, no 2 is there. That is why 2 to the power 0 has been rejected. So now in the first set, we are only having 2 to the power 1, 2 square and 2 cube. And from the other sets, as usual, whatever we have done in the previous one, when we were finding the sum of the all the divisors, that same method I have used. Only difference is that here I have not considered 2 to the power 0. Now you have understood why I have not considered that. Is it clear? So this is how we find out the sum of all the even divisors. Now the second question is, find the sum of all the odd divisors. Odd divisors means there in the divisor or in the factor, there should not contain any 2. So for that reason, in this case, what we will do, we will reject this one, we will reject this element, as well as we will reject this element. So from the set A, we are only going to take 2 to the power 0. Because again, I'm telling you 2 to the power 0 is 1. It means that if you take 2 to the power 0 with the other factors, guaranteed it is going to give us an odd divisor. That I have already explained. Therefore, the sum of all those odd divisors will be what? It will be 2 to the power 0 into 3 to the power 0 plus 3 to the power 1 plus 3 square, 5 to the power 0 plus 5 to the power 1, 7 to the power 0 plus 7 to the power 1 plus 7 square. So it gives us 1 into, this is 13, this is coming like 6, and this is our 57. So our answer is coming to, which gives us 4446. Is it clear? Now see one interesting thing. As we all know that the divisors are either even or odd. So the sum of the even divisors, we got 62244, and for the odd divisors we get 4446. Now if we add these two, it is just for your mental satisfaction. If I add this to what we are going to have, we are going to have 66690. Am I correct? Now you see, this is what? This is the sum of all the divisors of 17640. And that exactly that answer we got here. Is it clear now? Is this clear to all of us? Now we know how to find out the sum of even divisors, as well as we know how to find out the sum of all odd divisors. Now, what is the sum of all the proper divisors? Proper divisors means you have to eliminate the improper divisors. And the improper divisors of 17640 is 1 and the number itself. Yes or no? 1 and the number itself. So now you see, we are having 66690. This is the sum. This is the sum of all the divisors. Now if we subtract from here 17640 plus 1, what we are doing? We are simply eliminating the number itself and 1 from the sum of the proper divisors. So the sum of all the divisors of 17640. If we subtract it from there, we are going to have what? It's 49049. Okay? So this is what? This is the sum of all the proper divisors. So how to find out the sum of all the proper divisors? Simply, what is proper divisors? To understand that, we must know what is improper divisors. Improper divisors are 1 and the number itself. So from the sum of all the divisors, if we simply subtract the number itself and 1, we are going to get the sum of all the proper divisors. That's exactly what we have done here. Is it clear? Okay, so now this part is over. So now we are coming to this part which states that find the number of ways in which the given number can be expressed as a product of two divisors. Okay, product of two divisors. So to understand this, let me just take our previous example, which was 60. And 60 was written as 2 square into 3 into 5. And the divisors were 1, 2, 4, 5, 6, 7, 8, 9, 10, 12, 15, 20, 30, and 60. So there are 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 divisors here. Now look at very carefully. 12 divisors. Now I have to write this 60 as a product of two divisors. Now see this one. If I multiply 1 with 60, you are going to get 60. If I multiply 2 with 30, you are going to have 60 again. Again, 60 can be written as 3 into 20, 4 into 15, 5 into 12, and 6 into 10. Yes or no? So in how many different ways you have expressed 60 as a product of two factors or two numbers? It is your 1 into 60, this is 1, 2 into 30, 2, 3, 4, 5, and 6. Yes or no? So how many number of ways are there to express 60 as a product of two factors? There are 6 ways. How we got? What was the total number of divisors? It was 12. And when we are expressing the number as a product of two numbers, I mean two factors, then how many such ways are there? We got 6 ways. How we got? It's simply 12 divided by 2. So in this case, the total number of divisors divided by 2 will give us the total number of ways when a number can be expressed as a product of two divisors. Yes or no? Product of two divisors. In this case, the total divisors was 12. So the total number of ways in which this can be expressed as a product of two divisors is divided by 2. That is 6. And that's exactly what we got here. Is it clear? So now we can apply the same thing in our problem. In this case, the total number of divisors, it was 72. Let me just calculate once again. Total number of divisors will be 3 plus 1, 2 plus 1, 1 plus 1, and 2 plus 1 again. So it's coming like 4 into 3 into 2 into 3. So it is 72, right? So how many number of ways are there when this number can be expressed as a product of two divisors? It will be 72 divided by 2, that is 36. Am I correct or not? Am I correct or not? Total number of divisors will be nothing but, when it can be expressed as a product of two factors, the formula is what? Number of divisors divided by 2. Whenever they ask to find out how many ways are there in which it can be, the number can be expressed as a product of two factors, all we do is we simply find out the total number of divisors divided by 2. That's it. Now there is a big question. If it so happen that the total number of divisors which is coming is odd. Let me take an example. Let me take a number like 2 square into 3 square. This is basically 36. Now, total number of divisors here will be what? 2 plus 1, 2 plus 1, so it gives us 9. And 9 when divided by 2, that gives us a fraction. That is not possible. That is not at all possible. So in that case, what to do? Let me just do it analytically first. What are the factors of 36? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then it is coming like 18. Then it is coming to 36, right? So now you see, if I want to express 36 as a product of two divisors, if we multiply 1 with 36, we are getting 36, okay. 2 with 18, no problem. 3 with 12, no problem. 4 with 9, it's okay. But what about the 6? What about the 6? Big question. What about the 6? Now see, 36 can also be written as 6 into 6. Tell me yes or no. It can also be written as 6 into 6, which is actually not considered here. If we try to analyze the thing, in this way, we will see that there is a factor 6, which when multiplied with the same number, gives us that number itself. But since we are not getting 2, 6 here, it is not possible to get 2, 6 when we are writing the divisors. But 6 into 6 gives us 36. So we have to consider that part also, which is basically we have not considered. That is why in this case we are getting 1, 2, 3 and 4 such ways of expressing 36 as a product of two divisors. But this 6 is not coming into the picture. But 36 can also be written as 6 into 6. So which must come into our consideration. Therefore, total number of ways in this case will be what? It's not only 4, it will be 5. Yes or no? What are those numbers? It will be 136, 1 into 36, 2 into 18, 3 into 12, 4 into 9. Yes or no? 4 into 9 at the same time, 6 and 6. Okay, so we are actually having 5 such pairs. But from here, how to get it? We got the total number of divisors as 9. So what we will do, in this case, we will simply add 1 with the total number of divisors and then divide it by 2. So we are actually having what? In this case, we are having 5 such ways. Now the question comes, sir, when this thing occurs? This thing occurs when the number, be careful, try to make a note of this. This thing happens only when the number which is given to us, the natural number which is given to us is a perfect square. So if a number, natural number n is a perfect square, remember this, perfect square, then the total number of ways of expressing that number as a product of two divisors will be n plus 1. I'm sorry, not n. If the total number of divisors, let us denote it by d. d is what? Total number of divisors. Okay. So total number, when n is a perfect square, the total number of ways of expressing this number n as a product of two divisors will be the total number of divisors plus 1 divided by 2. But when n is not a perfect square, In that case, the total number of ways which n is expressed as a product of two divisors will be d by 2. That's it. Is it clear to all of you? Whenever they asked you to express the number which is given to us as a product of two factors or two divisors, all you do is you simply check whether that number is a perfect square or not. If it is a perfect square, then you find out the total number of divisors, then simply add 1 divided by 2. That will give us the total number of ways in which that number can be expressed as a product of two numbers. But if you find that n is not a perfect square, then simply find out the number of divisors and then you divide it by 2. Because until and unless the number given is a perfect square, you are not going to get the total number of divisors as odd. Are you getting my point? You will never get the total number of divisors as odd. So odd occurs only when the number is a perfect square. And in that case, you simply find out the number of divisors plus 1 divided by 2. That's it for perfect square. Is it clear to all? Okay, so we have done this sum. Number 10. Okay, so now let's move for the next problem. So in this question, they have asked for find number of ways in which the number 17640, the number is same, 17640 can be expressed as a product of two divisors. This sum we have already done. Expressing a natural number as a product of two divisors, we have done. But now they are adding a new condition, which are relatively prime number. Now the very first question that comes in our mind, what is a relative prime number? See, two numbers are said to be relatively prime number or co-prime number. All are same. Co-prime number and relatively prime number, they are same. So two numbers are said to be relatively prime number or co-prime number when the GCD or HCF between that two numbers is 1. That is, there is no other term common in that two number other than 1. Then we call that two numbers are co-prime or relatively prime. Not necessarily the numbers has to be prime number. No, I'm showing you. Suppose if I say 4 and 15, these two numbers are relatively prime number or co-prime number. Why they are so? Because the HCF or GCD between 4 and 15 is 1. But you see 4 and 15, individually, if you consider, they are not the prime numbers. And we don't need it also. It is only co-prime when the GCD or HCF between the two numbers is 1. That's it. So now you have to find out how many numbers are there, how many ways are there of expressing this natural number as a product of two divisors which are relatively prime. Okay, so let me just take our old example, which is your 60. Now, 60 can be written as like what? 2 square into 3 into 5. So again, let me just draw 3 sets. It is better to understand if we go for, doing the problem with set thing. 2 to the power 0, 2 to the power 1, 2 square. 3 to the power 0, 3 to the power 1, 5 to the power 0, 5 to the power 1. Okay? Now, the question is, we have to express 60 as a product of two divisors which are relatively prime number. Now, if the question would have been, express 60 as a product of two divisors, we can easily do that. We will find out what is the total number of divisors or factors. That is easy to find out. From here what you will do? You will simply say 2 plus 1 into 1 plus 1 into 1 plus 1. So that gives us 12, right? So 12 divisors are there and it is not a perfect square. Therefore, total number of ways which 60 can be expressed as a product of two divisors will be divided by 2, which gives us 6. That's a straightforward question. But in this case, we have to find out those ways where this 60 can be expressed as a product of two divisors, but they are relatively prime. Now think about it. If I want to get a prime number, if I want to get relatively prime number, then I cannot use 2 to the power 1 in our product. Why? In the product, I cannot use 2 to the power 1 because you have to make 60 by using two products of two numbers. Now, if I take 2 to the power 1 in one factor, so naturally the other 2 will go in the other factor. Yes or no? If 1, 2 is taken in one factor, where does this another 2 will go? Because you have to use both the 2's. You have to use two 2's. So 1, 2 I have taken for one factor. What about the other 2? It has to go in some other factor. Now the moment it goes to the other factor, you are having common ratio, common GCD. The GCD between the two numbers will be 2 because 2 is common between them. So it no more remains a co-prime number. Are you getting my point? If you take, suppose if I say there is a number in which we are having, say, 2 to the power 0, 2 to the power 1, 2 square, 2 cube, like that, 2 cube. Now, in that number, and there are other primes also, let us say 3 to the power 0, 3 to the power 1, 3 square, 5 to the power 0, 5 to the power 1, like that. I'm just taking an arbitrary number. So here, if we use a product, actually the natural number is what? It is 2 cube into 3 square into 5. If you multiply this whole, you are going to get this natural number n. It is basically 8 into 9 into 5, right? So 72 into 5. It is 360, okay? Now, if I choose, let us say, in one factor, I choose 2 square. 2 square, if you choose in one factor, definitely you have to give another 2 to the another factor. And the moment you give that, the GCD between these two numbers will be 2. That is, there will be a common digit between these two numbers. Then these two numbers will no more remain co-prime. Yes or no? Have you understood this? So, in this case, I cannot share 2 to the power 1. Either I will select 2 to the power 0 or I will select 2 square. That's it. Why? Because if I use 2 to the power 0, 2 to the power 0 means it's 1. If I use 1 in the one factor, so obviously 2 square will go in the other factor. Now you check it, there will be no common term other than 1 between these two terms. So that is why either you take 2 to the power 0 or you take 2 square. Means either you have to take 2 to the power 0 or you have to take 2 to the power its extreme value. Are you getting my point? In this case, it's 2 square. You cannot take the numbers in between. I make you understand through this example. Now, in our case, what will happen? Set A will now contain 2 to the power, let me just draw 3 sets first again. Understanding this logic is very important. Otherwise, you will not, you will simply memorize the formula and you will do the sum. That at the end of the day, it will not going to work. Now, either I have to choose 2 to the power 0 or we have to choose 2 square. Either the minimum one or the maximum one. And not only for set A, for set B as well as for set C. Because in between number if you take, I have shown you the numbers, the two numbers will no more remain a co-prime numbers. So in this case, the options are this. Okay. So how many number of options, I mean, if we only take 2 to the power 0 and 2 square, how many number of such divisors you will get? Obviously from here you are going to have 2, 2 and 2. So it is coming like 2 cube, which gives us 8. But wait. So 8 is the total, according to our theory till now, 8 will be the total numbers of ways in which 60 can be expressed as a product of two divisors which are relatively prime number. That we have understood. Now let me do one thing. Let me just try to find out the two numbers which when multiplied get 60 from this one, from this 8. What are those? It can be 2 to the power 0, 3 to the power 0, 5 to the power 0. I am writing these 8 numbers. So now it is 2 to the power 0, 3 to the power 1, 5 to the power 0. Again 2 to the power 0, 3 to the power 1, 5 to the power 1. Again 2 square, 3 to the power 0, 5 to the power 0. 2 square, 3 to the power 0, 5 to the power 1. 3 to the power 1, 5 to the power 0. And 2 square, 3 to the power 1, 5 to the power 1. That's it. These these 8 numbers we are going to get. So 8 such pairs can be formed in this case. See, what are the pair? This is 2 to the power 0, 3 to the power 0, 5 to the power 0. That is, it is 1. 1 when multiplied with 60 gives us 60, right? Next is 5. This one is 5. So 5 when multiplied with 12 gives us 60. This is 3. 3 when multiplied with 20 gives us 60. This one is 15. So 15 when multiplied with 4 gives us 60. This one is what? This is 4. So it will be 15. This one is 4 into 5, that is 20. So multiplied with 3 gives us 60. This one is what? 4 into 3. So 12 into 5 gives us 60. And for this one, it's 60 into 1 gives us 60. Now you see, these are my 8 options. That is why I got the answer as 8. But, since it's a product of two numbers, tell me, 1 into 60 and 60 into 1, are they different or the same? They are same. Because 1 into 60 is same as 60 into 1. Similarly, 5 into 12 is same as 12 into 5. 3 into 20 is same as 20 into 6. So what we got? We actually got there will be 8 such co-prime numbers. I mean, the product of two numbers which will give us 60, which are co-prime to each other. But here we can see that exactly half of them, they have already repeated. Because to me, these are all same with this one. Yes or no? 5 into 12 is same as 12 into 5. Therefore, total number of such co-prime numbers which can be formed is not 8. It will be what? 8 divided by 2. So that is only 4 such pairs can be formed. And that is your answer in case of 60. Are you getting my point or not? Is it clear or not? Now let us try to create a formula out of this. Now suppose there is a natural number, and in that natural number there are primes like P1, P2, and this thing goes on. Let us say there are Pn to the power alpha n. Okay. So these are the product of primes. Now if the question is, in how many different ways you can express n as a product of two divisors which are relatively prime number. So you see, we are going to have n such sets For P1, one set, P2, one set, P3, another set. And this thing goes on for Pn, the last set. So there are actually n such sets we can form. Like here. Here it is 2 square into 3 into 5. So 3 sets were there. Similarly, here there are n primes. So there will be n sets. Now from each set, to get the product of two numbers which are relatively prime, you can only select items from every set in two ways. Either you will select the lowest one, P1 to the power 0, or you will select the highest one, which is P1 to the power alpha 1. So for every set, there are only two ways of selecting numbers. Tell me yes or no. So from this one, two ways, this one, two ways, this one, two, and this thing goes on for n times. All two ways. So total number of that will give us how much? It's not n actually. It is going to give us 2 to the power n. But this is not the total number of co-prime pairs that can be formed. The co-prime pairs will be 2 to the power n divided by 2. Just now I have explained, because the pairs will get repeated. Therefore, the total number of co-prime numbers will be 2 to the power n minus 1. 2 to the power n minus 1. What is n? What is n? N is the number of primes involved in the prime factorization of the natural number n. Is it clear to everyone? So here n is nothing but the number of primes involved in prime factorization of n. Yes or no? Okay. So we will remember now onwards. We have first understood the logic, and now we are going to remember this formula. 2 to the power n minus 1 is the total number of pairs which can be taken out, which when multiplied get the natural number n, and they are relatively prime numbers. So in our case, in our problem in this case, it's 17640. Again, this can be written as, we have already done this, 2 cube, 3 square, 5 to the power 1, and 7 square. So how many number of primes are there? There are 4 primes involved in prime factorization of 17640. So total number of ways in which this 17640 can be expressed as a product of two divisors which are relatively prime number will be 2 to the power 4 minus 1, that is 2 cube. So it gives us 8. So 8 such pairs are there. 8 such pairs are there. Yes or no? The answer is 8. Have you understood this? First, we have understood the logic. Then we have created a formula. So whenever they asked you for finding out the number of co-prime numbers which when multiplied gets the number capital N, the formula is 2 to the power n minus 1. What is small n? The small n is the number of primes involved in the prime factorization of capital N. Clear to all? Okay, let's move for the next problem. See this question. 10800. The n is that same number. 108, no, not the same number. It is now, it's a different number. Okay, that's great. So if we go for factorization, we will have 2 to the power 4 into 3 cube into 5 square. I have already calculated this and I am writing it. You people have to find out its prime factorization. So now the question is, now before doing anything else, what I do, I simply draw 3 sets. Because there are 3 primes involved, I am drawing 3 sets. Set A, set B and set C. Set A contains 2 to the power 0, 2 to the power 1, 2 square, 2 cube, 2 to the power 4. Set B contains 3 to the power 0, 3 to the power 1, 3 square and 3 cube. And set C contains 5 to the power 0, 5 to the power 1, 5 square. Okay. Now let us read the question. What is the first question? Find the number of divisors of the form 4n plus 2. 4n plus 2 means if I take 2 common, it is 2n plus 1. See, this one is an odd number. Okay. But here there is a multiple of 2 only. There is a multiple of 2 only. So what to do? Now I need only 1, 2. So from set A, I am going to select only this one. Because I need only 1, 2. Not 2 2s or 3 2s. No, I don't want that. I want only 1, 2. So that 1, 2 can be selected from this element. Because if this element is selected, only 1, 2 is selected. Okay, from this there is no restriction. Anything from this 4 elements can come. From this set also any one of the elements of these 3 elements can come. And from the first set only one element will come. Which will be of the form 4n plus 2. Are you getting my point? Are you getting my point? Because 4n plus 2 is a form 2 times 2n plus 1. So I need actually 1, 2. So 1, 2 will come from set A because there are no 2 present in other sets. So 1, 2 will come from this set A, which can be selected only in one way. And now the other element can be selected from B and C. So any element can come from B and C because they will be all odd numbers. Are you getting the point? Therefore, the total number of divisors which is of the form 4n plus 2 will be 1 into 4 into 3. That gives us 12. Is it clear to all? Okay, now let us come for the second one, which states, find the number of divisors which are multiple of 10. Multiple of 10. Now what to do? Multiple of 10. That means I need 1 5. This 5 I need, not only this 5, any 5. But I don't need this 5 to the power 0. Because if 5 to the power 0 is there, you see, in 10 we are having 2 into 5. So I need at least 1 5 and at least 1 2 to make this 10. So I cannot use 5 to the power 0 in this case because 5 to the power 0 gives us 1. So we will not get 5 anymore in our product. Therefore, the only 2 elements can be chosen from set C. Tell me yes or no. Either it is 5 to the power 1 or it is 5 square. Because in both these cases we are going to get 10. And from set A, so from set C we are going to have 2 elements. Any one of these 2 elements. So that can be selected in 2 ways. Now from set A, I cannot choose 2 to the power 0 again. Because if 2 to the power 0 is selected, that is 1. So we are not going to get any more 2 in the factors. And if we don't get 2 in the factor, we are not going to get 10. So the divisors will never be a multiple of 10. So I have to reject this 2 to the power 0 in this case. So we are left with 2 to the power 1, 2 square, 2 cube and 2 to the power 4. So any one of this set, elements can come in our calculation. So there can be 4 ways of choosing one element from set A. And set B, there is no restriction. So any of this 4 thing can come. So total number of ways for the second case when the divisors are multiple of 10 will be 4 into 4 into 2. That is 32. Is it clear or not? Is this clear to everyone or not? Okay. So now let us come for the third one. They have said that the divisors are multiple of 15. Now you tell me. Divisors are multiple of 15. How you will get? When I have at least 1 5 and at least 1 3. So in this case what I will do, I will simply reject this 5 to the power 0. This I will not take. At the same time, I am going to reject 3 to the power 0 from set B. So, from set C, we can take any of these 2 elements. From set B, we can take any of these 3 elements. And from set A, there will be no restriction. Anything can come. Because it is not going to hamper us of not getting a divisor which are multiple of 15. That is why in A, there is no restriction. So any of these 5 elements can come. So total number of ways will be 5 into 3 into 2. So that gives us 30. Is it clear or not? Have you understood this or not? So whenever this kind of problem comes, you always find out that what is the form given in your question. And try to get that form from the elements in the different sets. That's it. Simply always, I'm telling you repeatedly, always try to do this kind of problems by drawing sets. It is going to help you immensely. Okay? Okay, let's move for the next problem. See this question. Find the number of lattice points. We have already done lattice points I have mentioned several times in our lectures what is lattice points. Lattice points are those points where both the ordinate as well as abscissa. I mean, if it is in the pair form like this, A comma B, then A and B both are integers. Like if I say 5 comma 2, this is a lattice point. If I say minus 5 comma minus 3, this is a lattice point. But if I say 5 comma 3 by 2, it is not a lattice point. Because here B is not an integer. So I hope lattice point is clear. Now you have to find out the number of lattice points on the curve xy is 2, 5, 2, 2, 5, 2, 0. Okay? How to do this? Now think about it. This sum is exactly same as the sum we have done. 2, 5, 2, 2, 5, 2, 0. The number which is given to us is a natural number. Now they are saying to express this natural number as a product of 2 numbers. 2 numbers means 2 divisors. So what is the question? You are simply going to find out the number of ways in which the given number, this big number, can be expressed as a product of 2 divisors. Okay? So now let me just write this big number 2, 5, 2, 2, 5, 2, 0 in prime factorization. We are going to have, I have actually already calculated this before, so I am simply writing it. 2 cube, 3 square, 5, 7 square, 11 into 13. Is it clear? Now the question is, how to find out the number of ways in which a number can be expressed as a product of 2 primes. Not two primes, in terms of 2 divisors. So I have learned that here you have to find out how many number of divisors are there. First of all, it is not a perfect square. That we can see because the powers are not even everywhere. Right? So the total number of divisors will be 3 plus 1, 2 plus 1, 1 plus 1. Is it clear? I hope it is clear. This is the total number of divisors. Total number of divisors. Which gives us actually so 4 3 is 12, 12 2 is 24, 3 2 is 6, 6 2 is 12. Which gives us, it's 288. Okay? So total number of divisors are what? 288. Now what I taught you, when we got this one, what I taught you, that during this multiplication, we have to divide the thing by 2. Why we have taught you in that way? Because there will be a repetition. There will be a repetition. Like in 60, 12 into 5 gives us 60. Again, in our calculation, 5 into 12 is also coming. That is repeated, and that is the reason why I have divided by 2. But in this case, I am not going to divide it by 2. Can you tell me why? Because 5, 12 and 12, 5 in case of 60, in that case, in the case of multiplication, if I simply ask you the product should be this, in how many different ways these two factors can be found? In that case, you are going to divide it by 2. That's no problem, because 5 into 12 and 12 into 5, to me, they are same. But when you are finding out the coordinates or you are finding out the lattice points, they are different. Why? Because 4, 15 and 15, 4, these are the two different lattice points. That is why I always say don't try to remember the formula. Before remembering the formula, you must understand the logic behind it. Otherwise, every time you will mess up with the problem. Okay, so in this case, if you divide it by 2, you are going to get wrong answer. Yes or no? Have you understood it why? Therefore, the total number of lattice points will be 288. No, there is another point. Lattice points means that A and B are the integers. Now, whatever these 288 types of pairs you got, I mean, these 288 lattice points you got, in everywhere, it can be replaced by minus also, because suppose if I get 2 and 5 as one of my lattice points, the other point can also be minus 2 minus 5. Because in that case also during multiplication, from here during multiplication you are going to get 10. In this case also you are going to get 10. Therefore, the negative values of the A and B, these has to be considered. Therefore, total number of lattice points will be not 288, rather it will be 288 into 2, that gives us 576, and that will be the answer for this problem. And this question is very, very important when we will do, coordinate geometry. There, in maximum cases, I have seen when I was solving previous year paper, that these people used to give questions on lattice points. They will give you, this is actually a rectangular hyperbola. xy equals to constant is a form of rectangular hyperbola. So they will ask you, find out the lattice points on a rectangular hyperbola like xy is something. The same question which is given over here. So in that case, you always remember this method. Whenever they are asking you to find out the points, lattice points, all you will do is what they are actually asking for. They are asking for a prime number is given to you. Express this prime as a product of two divisors. So what I will do, I will simply find out the total number of divisors, but whenever lattice points they are saying, you should not divide it by 2. Be very careful. And if the lattice point, if they don't mention anything in the question, so you have to take both positive as well as negative value. So whatever number of divisors you are getting, it will be multiplied with 2 to get the total number of lattice points. Why multiplied by 2? Because negative signs can also come in A and B. Is it clear to everyone? Have you understood this clearly? No question about it. So please try to remember the formula after knowing the logic behind it. Otherwise you will get, messed in questions. So that's all for today's class. I hope you have enjoyed the topic I have discussed today. So see you very soon in my next video. Till then, stay tuned to us and don't forget to subscribe, like and share this video. Thank you so much. Take a very good care of yourself.